When we continue about group 17, which is part 2 of relative reactivity of the elements as oxidizing agent. Alright, for today I will explain about the relating of oxidizing agent, okay, which is reaction of the elements with hydrogen, okay, and relative stability of the hydrides, which is hydrogen halide. Right. Okay, refer to our book. Right. So now here is the reaction of fluorine, chlorine, bromine and iodine with hydrogen to form hydrogen halides, okay, which is also called as hydrides. Right. So the reaction of all the halogen here is being reacted to the hydrogen gas. Okay, what is the product formed when it reacts? Okay, so here is the reactivity when going down the group 17 towards hydrogen gas. Okay, if you can see that hydrogen gas when react with fluorine gas, it will form hydrogen fluoride gas. Okay, so this reaction rapidly at low temperature in the dark. Alright. Okay, while hydrogen, okay, when react with chlorine gas, it will form hydrogen chloride gas. Okay, but this reaction will explosively occur in sunlight, which is okay under UV light. Then it will react. Okay, the second one, hydrogen gas when react with bromine gas. Okay, it will form hydrogen bromide gas. Okay, but this is needed the temperature and catalyst, which is 200 degrees Celsius, and using the platinum as a catalyst. Alright, finally is about hydrogen gas when react with iodine. Okay, we form hydrogen iodide gas, and this condition to be occur is temperature in a 400 degrees Celsius, and it also use the catalyst which is platinum. Okay, if you can see, the reactivity is decreases, okay, in the order of fluorine, chlorine, bromine and iodine. Okay, how to memorize this situation? Okay, refer to our analogy. Alright, so here is the example of halogen. So example, okay, when we want to accept the electron here, right, to receive the electron, because of the smaller size of halogen, so it has stronger attraction force, which is this nucleus higher tendency to receive electron. Alright, so means that the reaction is readily to form. Okay, so same goes to the this halogen lah. So for the fluorine gas, because of its smaller size, is readily to accept hydrogen, okay, which is electron in hydrogen. So means that it's readily to share the electron with hydrogen to form hydrogen fluoride gas. So that's why it's react rapidly, okay, which is it react rapidly. So this reaction occur react rapidly, right? So okay, all even okay in the dark, right? Okay, and then the second one is the chlorine is the larger size compared to fluorine, but it also can react with hydrogen. It's able to receive the hydrogen gas, but it must have UV light. Alright, okay, so with the presence of UV light, right, sunlight, which is sunlight, okay, the presence of the sunlight, so it will explosively react. Okay, the third one is a bromine. Okay, bromine, okay, because of its larger size, okay, so it will react with hydrogen gas, but okay, with the condition of 200 degree Celsius and with the platinum catalyst. Okay, and then same goes to iodine. Iodine also the largest size of halogen, so it can react with hydrogen, okay, but the higher temperature is needed, which is 400, and must using the platinum as a catalyst. Okay, so when going down the group 17, so the reactivity, right, of reactivity of fluorine, chlorine, bromine and iodine to the hydrogen become decreasing, right? Okay, so refer to our analogy that when we get extra principal quantum number, so the attraction force become weaker. So in order to form the reaction, so it's needed the higher temperature and also need the catalyst to form the reaction, right? Okay, while for let's say for fluorine here, fluorine because of its smaller size, okay, because of its smaller size, so it will have a strong attraction with the electron or with other molecule to be react. So it will react rapidly in a dark, even in a dark. This also shows that how fluorine is act as a stronger oxidizing agent, okay, and it's decreasing when going down the group, which is iodine is a weak oxidizing agent, then it is decreasing when going down the group. Okay, this equation it shows that fluorine is a stronger oxidizing agent, which is itself will be reduction. Okay, why it will oxidize H2 to form H plus, which is from 0 it's oxidized to form positive 1. So F2 is a stronger oxidizing agent. Okay, the next one, alright. Okay, I want to explain about thermal stability of hydrogen halides. Okay, because of that, the first reaction, it will form the hydrogen halide. Okay, now we want to know more about hydrogen halide. Okay, what is the properties of hydrogen halide? Right. So now, okay, so in terms of properties, okay, the first one is boiling point. Okay, so the boiling point of hydrogen halide, so actually if you can see that when going down the grade we form hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide. So this is the structure of hydrogen halide, which is it will share the electron to form the covalent compound. So these hydrogen halides, okay, are covalent compound. Alright, for the first thing, when we want to explain about boiling point, okay, what is the keyword, okay, of the boiling point? Right. So we must refer to the intermolecular forces of hydrogen halide. And if you can see that from among the hydrogen halide here, okay, hydrogen fluoride will form the what kind of intermolecular forces of HF? Okay, so it will form hydrogen bonding. Okay, hydrogen bonding, okay, which is it a stronger intermolecular forces compared to weak van der Waals forces. Okay, while okay, for hydrogen chloride, hydrogen bromide and hydrogen iodide, alright, so this okay contain of okay weak van der Waals forces, right, for the okay, so it contain of weak van der Waals okay forces. Alright, so from these intermolecular forces we know that the hydrogen fluoride is the highest boiling point since it have the hydrogen bonding, right? But then okay, how we want to measure the strength of HCl, HBr and Hi since it share the same intermolecular forces, okay, which is weak van der Waals forces. So okay, so since it share the same intermolecular forces, so we must refer to the size, okay, and as we know that when going down the group the size become okay increasing, right, the size become increasing, right? Okay, so refer to this diagram lah. Okay, so when going down the group the size become increasing, okay, hence okay when this hydrogen iodide gas consists of the larger size, so that okay, the total number of electron, okay, in this molecule are the highest. Okay, since it have the larger size. Okay, so it have the stronger weak van der Waals forces. Alright, because of the larger size. In explain about size, we also can calculate the total number of electron for each covalent compound, which is for Cl. Okay, we can calculate that you have 17 plus 1. So 1 plus 7, 17. So you have 18 electron here. Okay, and then for bromine, we have 1 plus 35. So we got 36 electron, and for iodine we have 1 plus 53, so we have 54, okay, electrons. So you can see that hydrogen iodide gas consists of the highest electron. So okay, so we can arrange the boiling point of hydrogen halide, okay, by increasing in the order, okay, which is, okay, because of this one is the smallest, okay, the smaller number of electron. So okay, HCl, which is weaker than HBr, okay, weaker than Hi, okay, and weaker than, alright, hydrogen bonding of hydrogen fluoride gas, so weaker than HF. So this is the boiling point of hydrogen halide. Second properties of hydrogen halide here is degree of polarization. Alright, okay, although that the hydrogen halide is a covalent compound which consists of covalent bond, okay, but it have higher degree of polarization because it have higher differences of electronegativity between H and X. Okay, since halogen have higher electronegativity. Alright, so you can see that, refer to our electronegativity chart here. Okay, you know that fluorine is the highest electronegativity, which is 4.0. Okay, followed by chlorine 3.0, and when going down the group 17 is getting smaller. Alright, 2.8, iodine 2.5. Okay, now, okay, refer to degree of polarization. You can see that hydrogen fluoride have the highest differences of electronegativity because fluorine have 4.0, okay, hydrogen have 2.1. So differences here is the highest one, okay, followed by hydrogen chloride, okay, and then hydrogen bromide and hydrogen iodide. So we can see that the degree of polarization of hydrogen halide become decreasing when going down the group. Alright, because of the electronegativity differences between hydrogen and halogen difference. Alright. Okay, so because of the higher electronegativity of halogen, okay, so make the compound of hydrogen halide a polar molecule. The third properties of hydrogen halide is all the hydrogen halide can dissolve in water to form hydrohalic acid. Here is the reaction involved, which is hydrogen halide react with water. Okay, it will form hydroxonium ion, okay, and halide ion. Alright, so the dissolution, okay, is involve the breaking of, okay, HX bond, okay, which is, okay, when going down the group, okay, the HX bond become longer, okay, hence, okay, the bond become weaker. So that's why HX bond get weaker when going down the group. So you can see that for HI is easier to be break, okay, compared to Br followed by HCl bond. So that's why the acid strength increases in the order of HCl, okay, is weaker acid than HBr, okay, and HBr is a weaker acid than HI. I, because Hi is easier to dissociate in water to form hydroxonium ion and iodide ion. Okay, so the acid strength increases, okay, followed by this order. Right, so we can say that Hi is a stronger acid compared to HBr and compared to HCl. Okay, how about the HF, hydrogen fluoride? Right, since hydrogen fluoride consists of hydrogen bonding and it is a stronger bond compared to other hydrogen halide, so hydrogen fluoride is a weak acid due to the strong, okay, weak acid, right, due to the strong bond, the strong HF bond. Okay, so we can follow like this lah. Alright, so the strongest one is hydrogen iodide. The fourth properties of hydrogen halide is thermal stability. Alright, so let's refer to our chem book. Alright, from our chem book here, it's it's tell that HX is decomposes on heating. Okay, it can decompose towards heat. Okay, but the stability of HX is different, okay, when going down the group. Okay, when we explain about thermal stability of hydrogen halide, since it is a covalent compound, okay, so we must refer to the bond length and bond strength. Alright, so when going down the group, atomic size of halogen increases, okay, hence the HX bond length, okay, getting increasing. Okay, the decomposition of hydrogen halides involve breaking the HX bond. So the longer the bond length, the weaker the bond, and the more easily the bond can be broken. Okay, so from this table, okay, how HX will decompose on heating? Okay, HCl, okay, it will decompose under 2000 degree Celsius. Okay, then it will decompose into hydrogen and chlorine gas. Okay, why hydrogen bromide? It will decompose into hydrogen gas and bromine gas under 600 degree Celsius. Okay, why hydrogen iodide? It will decompose, okay, under 200 degree Celsius. Okay, refer to this diagram. Okay, so you can see that the size become increasing. Okay, so when we talk about thermal stability of hydrogen halide, we must refer to the bond length, okay, which is covalent bond. Okay, covalent bond of hydrogen halide. Alright, so for the going down the group, so hydrogen iodide have a longer bond. So what happen is, alright, when the atomic size increasing, so it have, okay, longer bond, so become weaker. So the longer bond, okay, become weaker bond, hence it's easily to be break. So this bond is easily to be break. So that's why it's only 200 degree Celsius. We need only 200 in order to break the covalent bond, so it will decompose. Okay, why for bromine? Okay, in order to decompose, okay, we need the 600 degree Celsius because it's a shorter bond compared to Hi bond. Okay, followed by Cl. Cf is shorter bond compared to HBr, so we need 2000 degree Celsius in order to decompose. While HF is stable to heat. Okay, stable to heat. Okay, so here is the bond energy when going down the group, which is, okay, higher energy is needed to break the hydrogen fluoride, which is 562. Okay, and then followed by HCl 430, 370 for HBr, and for Hi, we need 300 kJ per mole to break the Hi bond. As a conclusion, okay, this is the overall, okay, to deduce about the reactivity of fluorine, right? Which is, okay, for fluorine is very reactive, okay, which is because of its smaller size, so it's readily to accept electron, okay, to receive the electron, okay, which is it will readily to share the electron with hydrogen, right? So if you look at the analogy, so because of the stronger attraction, so it's readily to receive another electron, right? But okay, we can say that fluorine is a reactive halogen, okay, which is a stronger oxidizing agent, okay, which is its good electron acceptor, okay, is the electron, so it's a electron acceptor. Okay, while, okay, for hydrogen fluoride, okay, gas, so here is, okay, when the electron is already bonded, okay, with the halogen, with the fluorine, okay, so like this, it's already bonded, so it's a very stable, because attraction force between nucleus of hydrogen and nucleus of fluorine is very strong attraction force. So you can say that because of the shorter bond, so it have a stronger bond. So that's why, okay, for hydrogen fluoride, it's a thermally stable, because it's very hard to be break, because of the strong attraction force between nucleus of hydrogen and nucleus of fluorine.